So what does it mean to do machine learning, or data science for that matter, or doing stuff with data? There's a whole bunch of steps in the process. Typically, you need to start by figuring out what is the problem you actually want to solve. Do I want to predict something? Do I want to understand something? How do I measure if I'm doing a good job? And then you need to collect the data, and this may already be done for you. Someone may meet with you and say, hi, I heard you took Computer Science 340. I have this data set. Can you help me out, right? So that might also happen, and then maybe steps 1 and 2 are already done for you. After that, there's often a lot of cleaning and pre-processing of the data that needs to happen. So it may not come to you in exactly the perfect form that you need in order to do what you want to do with it in terms of machine learning. And after that happens, you might want to explore the data. So try to get some intuition about it before you start modeling and bringing all these machine learning methods to it. So that's what we're going to talk about today, steps 3 and 4. And for the rest of the course, we will talk about steps 5 and 6. So I have a note about this later on, but maybe it's appropriate to say it now. I view this as a bit of a weakness of the course in the sense that I don't want you to finish 340 and think that it's all about training the model and these cleaning and pre-processing are not important or common or anything like that. We happen to concentrate the course on a particular step of this process, but if possible, try not to lose sight of the bigger picture throughout the course. Another thing you need to do at the end, which we also, at the end and throughout, in fact, which we also don't talk about much in the course, is communicating your results. And that's something that's very important as well. And if you can't communicate it, then there's no real point in doing it. OK. So today we're going to talk mostly about tabular data. By that I mean you have a table with rows and columns. So I've loaded in this Titanic data set about the ship Titanic. It's a popular data set for playing around with. And it has a whole bunch of rows, which we call objects or training examples or instances. There's a whole bunch of names for this, but each row is kind of a thing of interest. And then the columns are the features or the properties or the variables. So here we have people who are on the Titanic, whether or not they survived, something about their class, sex, age, how much their fare, and all kinds of things. So all of these columns are different features of the data set. And this head command here just shows the first few rows of a table. So there's actually a whole bunch more rows here in this Titanic variable. So by the way, if you want to follow along with this later or play around and you're wondering, what is SNS, what are all these different things, you can just scroll back up to the top of the notebook. I put all my imports at the top, so from there you can see what libraries I'm using, and so on and so forth. And some of those you might need to install if you don't have them. OK, so one question that we have is, what are the different data types? So when you were learning programming, you likely learned about the data types of integer, float, string. This is not exactly what I'm talking about, but something like that. Related idea. So we could have, for example, numerical features, a number basically, And I'm not talking about how it's represented in computer, like double versus single precision. I'm talking a little more conceptually. So we could have something that's a number, or we could have something that is a category, like what town did they embark on the Titanic in, or we can have all kinds of other things. So if I scroll back up for a minute, you can see there are some categories, there are some numbers, there are some binary items, which we can think of as categories, or we could think of as numbers, etc. And one thing that you're going to see a lot of in this course is that almost all the methods we talk about are for dealing with numerical features. So there are ways of dealing with other types of features, but we will focus the vast majority of the course on numerical features. So one thing we can do is convert categorical features to numerical. For example, what this line of code above was doing was taking the embarked feature, what town they embarked on, which was a category. There's a few different towns you can see there. And it was saying, OK, there's 3 different towns. I'm going to create a new feature for each town and just add that as a new column. And each object is just going to have a 1 in one of those cases. So if you boarded at Southampton, you're going to have a 1 under Southampton. You're going to have a 0 everywhere else. And this has several names, one of K encoding or one hot encoding. But essentially, what we're doing is turning this category into a little vector, or 3 new columns. And this is a very common thing that you're going to see in machine learning and in this course. And what I've done here is said, let's do that to all the categorical features in the data set, and then let's look at the shape of the data set. So if I did that same thing to all the categorical features, I would have 891 rows or objects and 280 features. So what we can now do, and we will do for pretty much the whole course, is we'll think of each of those 891 objects as a point in 280 dimensional space. So in fact, another name for feature is also dimension. Feature, variable, dimension. There's many names, but we're going to be doing a lot of geometrical thinking in this course of points in these high dimensional spaces and distances between them and separating parts of the space and making predictions on the space and all that kind of stuff. So, right. This is highly related to the fact that we added multivariable calculus a year or 2 ago as a new prerequisite for the course. Before I move on, any questions or comments so far? Yeah, Anna?
Yeah, I was wondering, so why don't we create an enum like from 0 to 2 and instead create separate columns for each town?
Right, so the question was, why don't we just create an enumeration type from 0 to 2? Why are creating new columns? That's a very good question. We want everything to be numerical. So if we just change the names from those towns to 0, 1, 2, they're still categories, just categories with new names, and we haven't solved the problem. But you might ask a different question is, why don't we just use the integers 0, 1, and 2, which is a reasonable thing to suggest. And the problem with doing that is it implies a certain kind of ordering on the categories. So you have these 3 towns, right? But once you map them to 0 and 1 and 2, you're saying this town is greater than that town is greater than this other town, but that's actually just made up. That's not a real phenomenon. And then when you start using machine learning methods that are expecting numbers and will take this ordering into account, you'll get results that you don't want. So the reason why we create these 3 columns is the order of the columns doesn't matter in general. These are just all the features we've collected. So there's no distinction between the 3 categories. It's just 3 new features, and we don't get this unwanted ordering. Yes, what's your name?
Guanqi.
Say it again.
Guanqi.
Guanqi.
And why would you put fair into domain variable? Because it's numeric variable
Maybe that was a mistake. Yeah, so the question is, why is fair in here since it's not a categorical variable? That's just a mistake. It doesn't need to be there. Yes, what's your name?
Sorry?
What's your name?
Dave.
Dave?
Is there any particular reason for us to use dummy variables instead of, say, numerical variables? Say, can we convert, I don't know, maybe Southampton, we can map Southampton to 1 and the other locations to 2, 3, 4, respectively.
So the question was, can we map the different towns to different integers? So I just answered that question. Luckily, the lectures are being recorded, so I invite you to rewatch it and get the answer to that question. Yes. Yes, what's your name?
Laura?
Laura.
What's the meaning of the one that has deck as either C or not a number?
Ah, great. Okay. What is the meaning of the one that has deck? So this is the deck on the ship, and we're just looking at the first 5 rows of the table. So there's actually decks A through F or something like that, and we'll explore that later. But it's a good point about the not a number. So that information isn't available in some cases, and this is one of many ways in which your data might not be clean when you get it. And we will talk about that a little bit today, and only a little bit in the course, maybe not as much as we should, but it's a very common issue to have missing data or missing features. Okay, so we're not going to talk that much about text in this course, maybe a little bit. But a very common application of machine learning is to process text. So a couple of lectures for now, we'll talk about how a spam filter works, say, in Gmail, which essentially has text as the input, right, the body of the email, and has the output, a category, spam or not spam. But there's a lot of text analysis. As you can imagine, there are chatbots. There's automatic monitoring of forums and documents and all these kinds of things. So if I started by saying we like to have the features as numbers because that's where we're most comfortable, how are we going to deal with this text? Here I just took some sentence online about UBC. It's a public research university, blah, blah, blah. So if we have a whole bunch of objects, each of which is a string like that, how are we going to deal with that? And there's more than one way of doing it. But one way of doing it is called bag of words. And essentially what that says is, let's just forget about the order of the text. Let's just consider the string as a bag of words. I just have all these words. And for each word will become a feature or a column. And I'm just going to ask, was that word present in that string or document? Or maybe how many times did that word occur? There is a Python library, or probably many, that does it for you. So I'm just going to run it. And I tried to print this out sideways, but didn't succeed. So you should imagine this in your head, turn 90 degrees, that those words are actually the column headings on this new table. They are the features. And the number is how many times did that word appear in that string or document. So you can imagine things getting pretty high dimensional pretty quickly because there are quite a lot of words in the English language, and maybe you don't want a feature for every possible word. For example, you only really care about the words that appear in your data, maybe, or maybe you want to reduce things even further to just not be overwhelmed with features. So if we turn this 90 degrees, this string of numbers here is the feature vector for one object, and we may have many such strings or documents forming this big table. And once we do this, then we can just plug it into your favorite algorithm for the course that is used to operating on numbers, or at least maybe you can do that. Dave?
Do we need to, say, normalize it?
Do we need to normalize it? So yes, and there are definitely ways of normalizing these vectors, including ways that have to do with how common the words are. To maybe if you see a word that's very rare, maybe that's extra important than if you see and is not such an important word. So yes, we don't get into that in this course, but certainly people do that. Okay, so yeah, I just want to emphasize how crazy this actually is, ignoring the order of the words, because all the meaning in a language is, there's so much meaning conveyed by the order of the words, I can't just jumble up a document for you and expect it to make sense. So this is a very crude way of dealing with text data, but it works surprisingly well. So maybe you want to run it on Amazon reviews and automatically decide if they were positive or negative. There are probably some words you can pick up on, like horrible, that will tell you it's a negative review, even if you don't know where that word appeared in the document. And yes, someone may write not horrible, and that might mess up your algorithm, and there are ways of dealing with that. But even though you're throwing away so much information here, sometimes throwing away information isn't that bad of an idea. Okay. And again, just keeping in mind this interpretation of things as a point in space. So if I have, I don't know, 12 words in my vocabulary here, now each string is a point in 12-dimensional space. Maybe I actually have 10,000 words or something like that. Okay, so here's an image I pulled off Wikipedia. There's a lot of nice high-level functions in Python. You will hopefully learn to appreciate the language if you haven't already used it. But for example, I haven't downloaded this image in advance. I just put the URL in, and this imread function just grabbed it and plotted it, and all kinds of conveniences like that. So here's an image of UBC that I hopefully cited appropriately from Wikipedia. And let's say the image was your input. So maybe you have millions of images, and for each one you want to classify, is this an image of UBC or an image of somewhere else? And you can imagine a whole lot of applications operate using images. Certainly on Facebook, for example, it's tagging people, and it wants to find out, are you in this image or your friends or something? So you're doing machine learning where your objects, your inputs, are images. So again, this is a very different data type than a number or a category or text. So how can we take this thing and coerce it into our vector of numbers that we're trying to use as our unifying data type? So one thing I can do is ask Python, what are the dimensions of the image? And we see this image happens to be that many pixels by that many pixels by 3. The 3 is for the 3 color channels, RGB. And I can say inspect some. So this is a 3-dimensional array. I can inspect some of the stuff in there, and it's telling me it's a bunch of unsigned 8-bit integers. In other words, numbers from 0 to 255, which are representing these intensities for the different colors. And here is some of what we're looking at. So maybe this is old news to you, or maybe you haven't thought about it before, but an image is just a whole bunch of numbers, in this case, a whole bunch of integers telling us different intensities. So there's a very straightforward solution to our problem in this case, which is let's just flatten it. So let's take the image and flatten it, and now it's whatever that number is, 8 million something long vector. So we've basically just taken that 3-dimensional array that represents the image and flattened it into a 1-dimensional array, aka a vector, and that is now our object, so our numerical feature vector. Any questions or comments? Dave?
Could you please explain the second line of the code? Is that referring to taking 3 slides from the...
Yeah, can I explain the second line of code? Sure. So this is, first of all, shorthand for this. So it's saying in the first dimension, give me the first... Yes, I'm slicing in 3 dimensions. So I'm saying from the first dimension, I want the first 2. In the second dimension, I want the first 2. And in the third dimension, I want everything, which is length 3. So I should be seeing 2 times 2 times 3 numbers.
What's the third dimension?
The third dimension is for color.
Oh, color.
Okay. Any other questions or comments about the image? There's many things that are worrying me about it that might be worrying you that we will get into eventually. For example, what if your images are different sizes? So we talk about having a table, right? But if you have different images of different sizes and you flatten them, they'll be different lengths, and we won't get into our nice tabular format. So there are different ways of dealing with that, such as taking standard size patches of images. You may also be worried that that's just a huge number, and how am I going to do all the stuff we're going to learn in this course in 8 million dimensions? And that's also something we're going to talk about. A third thing that may be disturbing you about this is, again, this issue of throwing away information, like with the bag of words. I used to know something, that this pixel was next to that pixel, was next to that pixel. There was this spatial information that I've just discarded when I've flattened the whole image. And that's something we'll talk about later in the course as well. Dave.
So when you are playing an image, is the image arranged something like, I don't know, RGB?
So yeah, Python has some convention for flattening things, either row by row or column by column or something like that. Yeah. Okay. Next topic. So, oops. Let me just fix that. Okay. So in the course, we usually assume the data is clean, which, as I was alluding to earlier, is usually not true. So there's a whole lot of things that could go wrong with your data set. There could be noise, or just incorrect values, or very unusual values, or missing values, or maybe duplicated values. Duplicated values is an interesting one because it maybe seems more harmless than the other ones here, but we'll talk about later why that can mess up some of the methods in this course. So, what have I done? Okay. So, there's a few approaches to dealing with non-clean data. One is apply data cleaning methods in advance, and one is use machine learning algorithms that are inherently robust to some of these issues and should hopefully kind of just work even if some of these issues are present. In the case of data cleaning, we may actually use machine learning to, for example, identify outliers and then remove them before doing an analysis. So there's this sort of loop sometimes of machine learning for machine learning. Okay, so how much data do we need? Common and unfortunate question. There is no single answer. This is a question I hear a lot. There is no single answer to this question. It depends so much on the application. It depends on the quality of the data. It depends on how well you need to do. Is 95% accuracy good enough? Maybe it is for some applications, but maybe if you're in a hospital and the person will die if you make a mistake, then 99.99% accuracy is still not good enough. So there are so many factors that determine how much data you need. More is usually good, for sure. And it's impressive how much you can do with fairly simple algorithms if you just have sufficient data. Although you can imagine with more data, you also get into scaling issues. What if my data set doesn't fit into memory and I need to move into the distributed computing paradigm and the challenges that come with that, etc. So there's a lot to think about there. Sometimes people talk about if you have this many features, you need this much data, like 10 times the number of objects versus features. Personally, I don't like that. It kind of makes features look like the bad guy. If I add another feature, oh no, I have to do more work to collect more data. But in a way, that's kind of backwards because features are your friend, right? If you're trying to predict something, the more you know, great, I have more information. Maybe that information will help me predict what I'm trying to predict. So the reality is a little more nuanced. Perhaps you need more data to effectively make use of more features, but I don't want you thinking that more features are somehow a bad thing that needs to be balanced against in some way. Okay, so another thing we can do is transform our features in various ways, as we've been doing. So, for example, let's say we talked earlier about the deck on the Titanic. So maybe there are just very few instances of people on certain decks, but actually whether they survived, it was really more of a question of were they below some part of the ship and were they above some part of the ship, and maybe that's really the key factor. So what we can do is count how much of each deck we have, and here in this particular case we only have a few examples on deck G. And so one thing we could do is say, well, why don't we combine decks A and B into, let's call that the upper part of the ship, and all the rest we'll call that the lower part of the ship. So we could do something like that. And I'll just scroll to the right. So now I have this new feature on the right that's called upper that was generated from the deck feature. And maybe that'll actually be more useful because we have more examples of upper and lower, whereas our data was very spread out between the different decks. And just a little note here that I had not handled the not a number issue properly so far here. So another thing we may want to do is feature selection, and we're going to talk about this a lot in this course. So what I've done here is I've said, let's take the index, which is just the count 0, 1, 2, 3, and so on, and let's make that into a feature called ID. So in this new table at the end, I have this new feature called ID, which is basically a meaningless feature. So another example that Mark had is maybe you were trying to predict something about students in the course, and you had their student number or something like that, right? So it's just some arbitrary number. It's not going to be useful in predicting what you want to do. However, when we do machine learning, we work with a finite amount of data. So if we only had 10 students to work with, it might happen by our bad luck that the ones with higher student numbers got better grades. And so the algorithm you're running might decide this student number feature is a great predictor for success in the course, so I'm going to use that as my primary predictor. And then when you go to predict in the next year, you get useless results because that learning that you did was an artifact of having a finite small amount of data to learn from. So many of the problems we're going to talk about in the course would not be a problem if you had an infinite amount of data to learn from. And that finiteness, I don't know if that's a word, but this property of having a limited amount of data has a whole lot of consequences, and a very important part of this course will be deeply understanding what those consequences are and what we can do about it. So feature selection says, well, maybe we can try to identify features that are or aren't useful in the task we're trying to do, and maybe we can just pull out those features that aren't useful in advance. For example, this made-up ID feature here. So as you can see, the situation is complicated. I was just saying earlier that features are not the enemy, and now I'm saying they are the enemy, and the message is that they may or may not have predictive power if you're trying to predict something. They may or may not be useful, and assessing that is something that we're going to study in this course. Dave.
Do you usually remove the, I don't know, the old features?
Do we usually remove the?
Old features. Say, so previously we have created some new features. So,
Oh, I see. Dave is asking if I say aggregate a bunch of features or do one of these transformations, would we remove the previous one? So yes, we would typically do some transformation to get some new features instead of the old ones. I may not have done that in all the demos. Yeah. Okay, so something we're not going to be doing much of in the course, but that it's worth being aware of is binning features. So turning numerical into categories. As I mentioned earlier, we usually like to deal with numerical features, so we don't do that much of this. But for example, if you look at the age variable of the people, the first 5 people on the ship, you have all these different ages. So I could make these bins from 0 to 20 years old, 20 to 30 years old, and above 30. And so I could create, again, this 1 of k encoding, where for each age I instead just indicate which bin the person is in. And that may be useful in certain applications, but as I mentioned, we're not going to be doing much of that in this course. Okay, so another thing we can do is sometimes we have numerical features already, but we want to do some kind of transformation to them before we proceed with our analysis. So Dave had mentioned normalization. That's a very common type of transformation we're going to do. Sometimes it's very important for our features to be normalized, and we'll be talking about that actually quite soon. In one of the lectures next week, we'll talk about when normalization can be very important. But just as a toy example, I could take the fare people paid, and I could take the square root of it. In this particular case, I'm not exactly sure why I want to be taking the square root of how much someone paid to ride a boat. But it has happened to me that this has been useful, especially in the case of things being negative or non-negative and wanting them in a certain way. So for example, sometimes in an analysis, I need my numbers to be non-negative for some reason, but they're all kinds of numbers, so I just take exp, and that will bring everything into the non-negative part of the space. Or on the contrary, it's also happened to me that I have some statistical model. It assumes something where it makes sense for the variables to be negative or not, but they're positive, so then I take the log or something like that. So it is sometimes useful to transform the variables to fit with the type of model that you're using. And we'll actually be talking about that with respect to polynomials at some point. Yes, what's your name?
Ali.
Ali.
When you do some sort of transformation or aggregation of data, do you usually want to keep the original as well?
So that's what Dave had asked about keeping the original. So yeah, when you do some kind of transformation, typically you would replace the original version with the new version. Okay. So exploratory data analysis, or EDA. How do I look at my data? Well, this can be hard when we're talking about things in 10,000 dimensions or 1,000,000 dimensions, right? So with the Titanic, it wasn't that painful to just look at the table. But even then, we don't really have a sense for things. How old were the people on the Titanic? What fraction of people did survive or not survive? It's very hard to understand that just by looking at a giant table. And that's not even that bad of a case because the data set is relatively small. So we want to generate visualizations or statistics that will give us very quick and useful intuition other than just looking at a giant text file or whatever it is that you might have. So in terms of summary statistics, meaning statistics that summarize your data, we could, for example, say for the deck, what fraction of people are on each deck? And then immediately we start to understand, okay, here's the distribution across the boat. So those are the frequencies. And we could also ask what is the most popular deck, and it's deck C. So that would be the mode of the distribution. Moving on to continuous values, there's all kinds of things you can calculate about a set of numbers. So you are surely familiar with the average. There's different types of averages, mean, median, quantiles, so different fractions of the distribution. We can talk about minimum, maximum, and all these kinds of things. And if we start computing them, maybe we start to get a sense of how much did people pay on the Titanic. Again, we should be a little more careful than I'm being about missing data and all that kind of stuff. But we can say, okay, the 25% of people paid less than 8, and 25% of people paid more than 31, and the middle 50% paid between 8 and 31, and all that kind of good stuff. So we don't need to scrutinize every single one of these, but I'll just run the code for you. So the variance and standard deviation are the measures of spread. How spread out is a distribution of numbers, with the standard deviation being the square root of the variance. So one thing I wanted to point out is that some of these summary statistics can be completely derailed by extreme values or outliers. And you may have seen this in your statistics course or wherever, but if I create this list of numbers here, and the very last number is much bigger than the rest, what I can do is I can compute the mean of the whole list of numbers and the mean excluding just the last number. And you'll see that they're very, very different. So just including that last number has totally changed the mean quite a lot. And this is okay if it's true, but it's bad if the 200 is a mistake or an error or something like that, and it's messing up our statistics. So likewise with the standard deviation, if I include or exclude the outlier, I get very different results. Whereas the median is robust to this because it just says I want a point where half the numbers are on one side and half are on the other side. So if this is the median and I take some number over here and make it 1 billion, it doesn't change anything. Yeah, your name?
Fred.
Fred.
This might be a deeper question, but when do you know if you can remove an outlier?
So we will have a lecture on outliers, and then we will talk about when to remove an outlier. Your name?
Raghav.
Raghav.
Yeah, mine was a similar question. I was going to ask, when we have a very large data set, how would you identify an outlier?
When we have a very large data set, how would you identify an outlier? So great question. I could also punt that to the outlier lecture, but in fact, even in the next few minutes, we will touch on that with certain types of visualizations can make that very clear very quickly. Yeah, your name?
Matthew?
Matthew.
Is there anything analogous to standard deviation that is more robust to outliers?
Is there anything analogous to standard deviation that is very robust to outliers? So yes, I would think that these interquantile ranges should be, because the quantiles are kind of like medians, but they still measure the spread of a distribution. Okay, 9 minutes left. So taking distances between feature vectors is an important thing. I will leave that for next week when we will talk plenty about distances. But for now, there are different ways you can compute distances, and that's all I really feel the need to say. Okay. So these summary statistics can be very useful, but they can also be very misleading. And there's this famous example called Anscombe's quartet, which is in fact even by default in this Python package, so I don't even have to input it or anything. And it's basically 4 different sets of numbers that have almost the exact same mean, variance, correlation, and linear fit, but when you look at them, they actually look totally different. So I'm a bit too zoomed. I guess that's okay. So here we have these 4 different data sets in the 4 quadrants, and when we look at them, they're just totally different, right, in their shape and structure and everything, but somebody crafted them just right. So when you do these, what is the average, what is the variance, they appear to all be exactly the same. And the point of this is just a warning that the summary statistic doesn't always tell the whole story, and is a bit of a segue into the last part of the lecture about visualizations. So you can play around with this after. If you don't believe it, it's all here. You can fire up the notebook, take the means, take the variances, and prove it to yourself. Okay, so let's talk quickly about visualizations in the remaining time. So we'll usually use matplotlib in this course, which is kind of, it's called that because it's based off the MATLAB plotting functionalities. Seaborn is this higher level library that's built on top of matplotlib. I will be mixing the two of them here. Personally, I tend to use matplotlib quite a lot, but that may just be out of ignorance. I'm not sure. So here's a basic plot in Python. Linspace, again, you can see they've copied a bunch of things from MATLAB. For those of you who have used MATLAB before, it just means 1,000 equally spaced points between 1 and 0 and 10. And then I'll just plot cosine, just to say we can make regular kinds of plots. I'll also show you this iris data set, which has information about these iris flowers. This is a well-known data set. And I can ask things about different dimensions of the flower. And one thing I might want to do is make a histogram. So probably most or all of you have seen histograms before, but to answer the question of Raghav, if you were making a histogram, you might be able to identify outliers, for example, because you'll see this, and then way over here, you'll see a little bump that there's some extra value that's very. There's just one way that you might come across outliers. So these are the different lengths and how frequent they are. So that is a histogram. And this I also wanted to, in terms of your question, Raghav, a box plot is a useful type of plot which shows a whole bunch of things at once. So it shows the median in the middle. It shows the quantiles, so either 0 and 90 percentile or 25, 75. But it also shows outliers explicitly. So what we're looking at here is the fare people paid. And on the left, they didn't survive. And on the right, they survived. And now we can start to see some things. So we can see that for whatever reason, this person who survived paid a lot of money to go on the Titanic. But we can actually start to see things about the data set, even from this plot, right? We can see, well, I wonder if people who survive, if there's some correlation between surviving and paying more because maybe they were on higher decks, and we could start exploring that, computing correlations. But these types of plots are quite a compact way of seeing quite a lot of information, and they can be very useful. So I can scatter plot between the sepal length and petal length of the flowers. So now I'm just taking 2 features. So before we were just looking at 1 feature at a time. Now I'm saying we'll take 2 features, put one on this axis, one on that axis. And now again, I can see each point is an actual object or row, and I can try to see what's going on. Maybe there's a correlation, et cetera, et cetera. Any questions or comments? Yeah, your name?
Oliver.
Oliver.
So this would be only limited to like a 2-feature kind of set, since we can't really. Well, at least
would be limited to 2 features, but I have something that you're gonna like. So you can also make a scatter plot array, which says let's take all pairs of features, and for every pair, let's make a scatter plot. Oh no. Should work. There we go. So now for all pairs of features, this is a very fancy scatter plot array. but it's saying, okay, along the side you have all the different features, along the columns you have all the different features. And this has gone extra fancy on us and provided some extra stuff, like it's coloring based on the type of the plant, which is just some extra information. And along the diagonal, where you have a feature with itself, it's showing us this pretty looking histogram. But in a more basic form, if you had a not too ridiculous number of features, then you could do this kind of thing and try to eyeball what's going on. Are there any interesting patterns, clusters, all that kind of stuff. Yeah.
So just to follow up, so if we had a ridiculous number of features,
We will get to that later in the course. What to do if you have a ridiculous number of features and you still want to look at your data. That's coming in maybe a month. Okay. So I said this earlier, but I have it here, so I'll just say it again, which is that this course focuses really on the modeling part of this big chain of things you actually have to do to successfully apply machine learning, data mining, data science, etc. And just, I'll try to say it once in a while because it does bother me a little bit. And I just want you to at least be aware that the course is focusing on a particular part of a larger process. So to summarize what we talked about today, we talked about the steps in data mining or machine learning. Let me just ask that people don't start packing up as a general thing in this course, because otherwise the summary is, this more triumphant moment for me, and if people are starting to pack up, then I kind of lose my groove. So we talked about different types of data, so you could have categorical, you could have numerical, text, images, all kinds of things, and in each case, can we coerce that into a format that we know how to do something with? We talked about transforming features in various ways and also exploring things, both with statistics and also with visualizations. And as I mentioned, we will continue with visualizations towards the end of the course, using machine learning to produce visualizations for higher dimensional data. So that's all for today. Have a good weekend, and I'll see you Monday.